Okay, now welcome to video class number 20, and in this video we are continuing with the properties of is a transform. So in the last video we have done some problems, as well as we have studied some four important properties, and we also have seen how to apply those properties to arrive at immediate solutions. Now this is the fifth property, and this property is named as multiplication by n property. What does that mean is, if you have an x of n whose z transform is x of z, then there can be, you can multiply x of n by n. Here n is not a constant, n is a variable, the variable. Okay, it is similar to, similar property we studied in the Laplace transform of the form t into x of t, and we found out in the frequency domain that's differentiation. So similarly, the z transform of this is also going to be minus z into dx of z by dz, and which also shows that, as I have mentioned earlier in this class, that x of z is also a continuous variable or continuous function. Even though x of n is discrete, its frequency domain is continuous in nature, just as the discrete time Fourier transform. In the discrete time Fourier transform also, we have seen that even though the discrete time Fourier transform is the Fourier transform of a discrete time signal, the transform is going to be continuous nature. So similarly, x of z is also continuous, and because of that you can have an operation like dx of z by dz. Now how to prove it? How to prove this proof? Okay, so start from the basic expression. When you write the expression for this, you can write this as n is equal to minus infinity to plus infinity, n into x of n z raised to minus n. Okay, now if I am simply multiplying and dividing by z, this expression, that is z into z raised to minus 1. What is this? This is actually equal to 1. Z into z raised to minus 1 is equivalent to z by z into sigma n is equal to minus infinity to plus infinity, n into x of n z raised to minus n. Right. Now what must be this? So I am taking this, keeping this z outside, I am taking this z inverse into the summation. Right, there is no problem in taking that. So this is n into x of n into, combining this z raised to minus n and z raised to minus n, you can write this as minus n minus 1. Right. Okay. Now the next line is z into sigma n is equal to minus infinity to plus infinity x of n into, okay, n times z raised to minus n minus 1. So just have a closer look at this. Is it actually a result of anything? So what happens if you say, just listen here, what happens? So you have a variable called as z raised to minus n. So what is dz raised to minus n by dz? What will happen to the derivative of this? How will you take the derivative of this? This will be, minus n into z raised to minus n minus 1. Okay, so that means if this is equal to the derivative of this, what is n into z raised to minus n? So n into z raised to n minus 1 will be equal to the negative of dz raised to minus dz. So you can replace this by, okay, so in the next line you can rewrite this expression as n is equal to minus infinity to plus infinity x of n. You can rewrite that as negative d z raised to minus n by dz. Right. Okay. So okay, now this z is, anyway, you cannot bring this z to this derivative operator because it's well outside, but you can bring this summation. There is no problem in that. So you can write this as d by dz summation because the summation has nothing to do with this derivative, so there is no problem in bringing this x of n into z raised to minus n, and you can bring this minus outside. Okay, so what is this? This is actually the z transform of x of n, right? That is represented by x of z. So this is minus z into d by dz of x of z, right? Okay, fine. Okay, then what will be the say you can have a general expression of that. If suppose if it is of n raised to k into x of n, what will be the z transform? The z transform will be minus z into d by dz, the whole raised to k. What's the meaning of that? This will be minus z raised to k into you should take how many derivatives of z? X of z, k derivatives. Say for example, if it is n square into x of n, what you need to do is you need to multiply that by minus z square into, take how many derivatives? 2 derivatives, dz square of x of z, right? Okay, fine. Okay, now next is the convolution property. So in order to explain convolution property, you need to assume minimum 2 signals, x1 of n and h of n, x of n and h of n, whose z transform is given as x of z and h of z. And the convolution property states that the convolution of these 2 time domain signals, if you convolve this, and that convolution will also be another say let us call this as y of n. So that will be another time domain signal, so it can also have an z transform. That z transform is nothing but it is the product of these 2. So you are very much familiar with this property because we have been studying for about this under different topics. Okay, so now let's see what is this z transform of x of n in star h of n. Okay, so this is equal to, what is the summation? Summation as n varies from minus infinity to plus infinity into the convolution. What is the result of convolution? Convolution is nothing but k is equal to minus infinity to plus infinity x of k into h of n minus k, okay, the whole into z raised to minus n. Okay, now on to this I am simply say n is equal to minus infinity to plus infinity. All of you please listen, you must be very cautious when you do this. It's a simple technique where n is equal to x of k into h of n minus k into, okay, so I'm just putting in this z raised to minus n, I'm just putting some z raised to minus k and z raised to k. Okay, z raised to plus k and z raised to minus k. There's nothing wrong in that because zk by zk it's 1. Now what if I combine these together? I am going to combine. In the next step I am going to combine this, taking the negative sign outside. So this will be, okay, so you can say that. Now what happens is in the next step you can interchange the summation as well in this form. Say k is equal to minus infinity to plus infinity. So I am taking this x of k outside and just an interchange of the summation. There is no problem, technically no problem in interchanging this. H of n minus k. Now what if I combine these together? When I combine this together, you will get z of minus n minus k, right? N minus k into z raised to minus k, right? And in the next step I am bringing this z raised to minus k over here. K is equal to, because this has nothing to do with this summation, so k is equal to minus infinity to plus infinity x of k into z raised to minus k sigma n equals minus infinity to plus infinity h of n minus k into z raised to minus of n minus k, right? Now putting n minus k is equal to L. So this expression becomes k equals minus infinity to plus infinity x of k into z raised to minus k into sigma. What about this n minus? So from this you can say that n is equal to L plus k. Okay. I mean, when you put n minus k is equal to L also varies from, as n varies from n is equal to minus infinity. So you can put L is equal to minus infinity to plus infinity, and this will be h of L into z raised to minus L. So it is same as writing what? Same as writing sigma n is equal to minus infinity to plus infinity h of n into z raised to minus n. This is also same as writing n is equal to minus. So these are what? What is this? This is a, yeah, this is actually x of z. This one is actually your h of z. So this is the product of x of z and h of z. So that's the convolution property of z transform. Okay, now let's move on to study what is, if the z transform of x of n is x of z, what is the z transform of x of n by k? Okay, now the z transform of x of n by k is equal to sigma n is equal to minus infinity to plus infinity x of n by k into z raised to minus n. So this is actually equal to, you can put n by k to be equal to L. So L also varies same in the same way. So you can rewrite or change the limit to L minus x of L into what is n. From this n is equal to Lk. So z raised to minus Lk. Now you can just separate this z. Okay, so sigma L is equal to minus infinity to plus infinity x of L into, okay, now you don't need to separate, rather okay, you can have this is the same thing can be written as z raised to k minus L, right? So this is of the form n is equal to minus infinity to plus infinity x of n into some quantity raised to minus L. Wherever we find such a, you will represent that function f as the function of that variable raised to the negative of that. So the variable here is, instead of z you have z raised to k. Okay, so that's it is proved. So the time expansion, this is called as a time expansion x of n by k, and you just there is a condition that this k has to be, that n must be a multiple of k. Okay, otherwise this is going to be 0. So this is defined only in this condition, n must be the multiple of k. Okay, fine. Okay, now the next one is the 8th property, which is the conjugation property. You have x of n, whose z transform is x of z, then x star of n. When this conjugation property applies is x of n, when it becomes a complex signal of the form a plus jb. That means there must be an x star of n, which is its conjugate. This is of the form a minus jb. Now just straight away finding out the z transform of x star of n. What is z star x star of n? This will be sigma n is equal to minus infinity to plus infinity x star of n into z raised to minus n. Okay, now what I am going to do is I'm just taking the star outside. Okay, so n is equal to minus infinity to plus infinity. If I am taking the star, now that is, it's equivalent to star into star is without star, no, that is, it is the conjugate. Okay, so that means this is x of n, and here you will be having a z star of minus n, right? So what is this? This is going to be, as explained earlier, this sounds similar to, this is similar to what? N is equal to minus infinity x of n z star raised to minus n. So the resulting function inside this bracket will be x of not z star, but there is a star outside. So this will be x star of z star. Okay. Okay, now coming to the 9th property, which is the complex convolution. Now the word itself suggests that this is a convolution taking place in complex plane, that is in the Z domain. Now what does this complex convolution says? So it is actually the dual of the convolution in the convolution property which we have studied before, right? So in the convolution property of Z transform, we studied that when you convolve two time domain signals, that is say x1 of n and x2 of n, then what we studied under the convolution property is it is the transform of x1 star x2 of n will be simply the product of x1 of z and x2 of z. Now it is the reverse meaning you are taking the product of x1 of n and x2 of n. What's going to be the result? Obviously you can expect what? If it is a dual, then you must expect a convolution operation in time in frequency domain. So that's what is the complex convolution wants to talk about. Now it is x1 of n into x2 of n. So this product is going to be another time domain function. So that means this will also be having an Z transform. That Z transform is given by this expression 1 by 2 pi j contour integration x1 of v into x2 of z by v into v inverse dv. Now my first aim is to prove that the Z transform of this product is going to be this. Okay, now let's move on to the proof. Now what does this proof states? So you are using this, in this step you are using the expression directly, that is x3 of z is given by sigma n is equal to minus infinity to plus infinity x1 of n into x2 of n into z raised to minus n. Now we have already studied I have already mentioned in the last video, I think it's in the 18th video, when I introduced the Z transform, I also specified about the inverse Z transform. So for a signal to retrieve, that is to get back the time domain signal, you have this this expression, that is the given x of z is multiplied by z raised to n minus 1 and performing a contour integration. By contour integration refers to a closed path or a closed path, and over that closed path an integration is performed, and that is a complex integration into 1 by 2 pi j. Okay, now we are making use of this equation for x1 of in this equation. Okay, now let's see what it is. X3 of z. So instead of x1 of n, we will be expressing that x1 of n as the using this expression we will be substituting the inverse equation in this in the summation, right? Now before moving into that, see in the expression we have seen a v and a z, both are the same. So z is a complex variable, similarly v is also a complex variable. So here v is said to be the ROC of what? ROC of x1 of z. Okay, so x1 of n is the x1 of z is the z transform of x1 of n. That means this v is nothing but it is the ROC, or sometime or it is v is exactly the same as that of a z variable. We have already defined z to be some r into e raised to j omega. Here v is defined as r into e raised to j theta, but in this case we simply take r to be equal to 1. Okay, so z and v is defined as e raised to j omega and e raised to j theta, meaning they are both are of the same format, or both are having the both are of the same characteristic, of the same characteristic. Okay, now if that is the case, now if you can replace this x1 of z by x1 of v, that's your Z transform. Z transform of what? Z transform of x1 of n. Now if x1 of z is known, you can straight away perform this integration, x1 of v into, instead of z you have v raised to n minus 1 dv. Okay, so under the summation, this x1 of n is replaced by this expression, by the inverse expression, that into x2 of n into e raised to minus n. Now you are just rearranging this term, rearranging in such a way that you are taking the sigma n is equal to minus infinity to x2 of n and z raised to minus n on one side, and 1 by 2 pi j closed integral x1 of v into v raised to n minus 1 dv. Now look at this. This v raised to n minus 1 can be written as v raised to n into v raised to minus 1. Okay. Now in the next step, what you do is you are changing the order of integration and summation. Okay, you can bring this summation inside this. So 1 by 2 pi j integral contour integral of x1 of omega, bringing this sigma n is equal to minus infinity x2 of n z raised to minus n inside this. And when it comes inside, it will be finding this v raised to n. That v raised to n can be represented as this z raised to minus n, and v raised to n can be written like this, right? So it is z by v. What is, when it comes at the numerator, it will be v minus 1. V minus 1 of minus n is v raised to n. So there is nothing wrong in writing like this, z by v raised to minus n, v inverse of dv, right? Now what is basically this? What is basically this? We have seen that sigma n is, say, we will call this sigma n is equal to minus infinity to plus infinity x2 of n into z raised to minus n. We will be calling this as x of z. So instead of z you have z by v, so it will be z by v. So that's it. So this can be represented as capital X of z by v. This is x1 of v, closed integral 1 by 2 pi j v inverse dv. Now this is your expression. We have proved that the z transform of this. Now why this is called as a convolution? I mean, you are not getting a feel of convolution by when you look at this. So what I am doing is, we have already defined that v to be e raised to j theta and z to be e raised to j omega, and for this dv you can find out dv. Dv is nothing but differentiating this with respect to theta, so that this becomes j e raised to j theta into d theta. Substituting all this in this equation, you will get an equation like this, right? 1 by 2 pi j closed integral x1 of e raised to j theta into x2 of e raised to j omega by, that is z by v, e raised to j omega by j theta into e raised to minus j theta and into j into e raised to j theta d theta. I have rewritten here again. So what you will get is this j and j get cancelled, e raised to minus j theta and plus j theta gets cancelled, resulting in 1 by 2 pi. I'll talk about minus pi to plus pi. Okay, x1 of e raised to j theta into x2 of e raised to j omega minus theta d theta. Now it sounds similar to x1 of theta into x2 of omega minus theta d theta, as theta varies from minus pi to plus pi y. This is an angular, so altogether it has to rotate from 0 to pi or from minus pi to plus pi. So this is circular in nature, so therefore this is this corresponds to the convolution in frequency domain. Hence the property is called as a complex convolution. Okay, next one is the Percivals relation. Okay, now under Percivals relation, again you consider two signals, x1 of n and x2 of n, whose z transform is x1 of z and x2 of z. Okay, now the difference is here this x1 of n and x2 of n is considered to be a complex signal of the form a plus jb. So there must be the conjugates of this as well. So now what does the Percivals relation shows? Percivals relation shows the z transform of what? Z transform of x1 of n into x2 of x2 star of n. Sigma n is equal to minus infinity to plus infinity x1 of n into x2 of n star. Okay, now to get this expression, we can basically start from this expression. What is basically this? This is actually sigma n is equal to, what is this? This is the complex convolution. Complex convolution is the z transform of x3 of 1, or in other words, it is the x1, it is the product, it is the z transform of this product. So you can use the basic expression as n is equal to minus infinity to plus infinity x1 of n into x2 of n into z raised to minus n, right? Okay, now if this is equal to this, so we will start from this, then what must be sigma n is equal to minus infinity to plus infinity. That is what I meant is, say, look at here. So this expression is actually equal to sigma n is equal to minus infinity to plus infinity x1 of n into x2 of n into z raised to minus n. Okay, now instead of this, if you have an x2 of n, what will be this expression? This is equal to 1 by 2 pi j into closed integral x1 of v into x2 of z by v into v inverse dv. Okay, this is what we have proved right now. Now instead of this, say there is only one change. I am starting with this. We need to to derive Percivals relation, we need to start from this x1 of n into x2 star of n z raised to minus n. What will be this? Okay, there is no problem here. 1 by 2 pi j into closed integral. Okay, no problem. Now you have x1 of v, right? x1 of v. Why? This is x1 of n. x1 of v is going to be the z transform of x1 of v. Okay, x1 of v is the z transform of x1 of n. So what must be x2? So this x2 of z by v is actually the z transform of x2 of n, right? So if that is the z transform, what will be the z transform of x2 of n star? x2 of n star will be, we have seen that, say from the conjugation property, I am just recollecting the conjugation property. Say if it is x of z, what is x star of n? What is the z transform of x star of n? That's going to be x star of z star. So that means this becomes x2 star of z by z star by v star, right? Okay, so using that you can straight away write the same expression. Okay, look at this. So this will be 1 by 2 pi j. The only difference is x2 star z star v star into v inverse dv, right? So this is your expression. Now we want to get an expression like this, that is z of sigma n is equal to minus infinity x1 of n into x star of n. Now this consists of, what is this? This consists of an z raised to minus n. So in order to get this, you need to evaluate this integral or this contour integral along z is equal to 1. What is the meaning of z is equal to 1? Z is equal to 1 in an z plane refers to a circle with the radius r. Z is equal to 1 means r e raised to j theta is equal to 1. That means this is magnitude is 1, so r is equal to 1. That means this is going to be a z is equal to 1 means r e raised to j theta equal to 1, r is equal to 1, meaning that this is a circle with the radius 1. So if you are evaluating this integral over this closed contour, that is at z is equal to 1, you can substitute z is equal to 1 here. Here also you can substitute. So resulting in sigma n is equal to minus infinity to plus infinity x1 of n into x2 star of n is equal to 1 by 2 pi j closed integral x1 of v into x2 star of 1 by v v inverse dv. This is actually your Percivals relation. Okay, now the next property is the correlation property. That's the 11th property. You have x1 of n and x whose z transform is x1 of z, x2 of n whose z transform is x2 of z. Then what is the meaning of correlation? Correlation, this is cross correlation, x1 x2 of L, where L is the time lag. This is the expression of correlation which we have seen earlier. Sigma n is equal to minus infinity x1 of n into x2 of n minus L. So this is going to be a function of L. That is what is called as a correlation, cross correlation. Now you can find the z transform of cross correlation. What is the z transform of cross correlation? This is given by x1 of z into x2 of z raised to minus 1. Now you must note the difference between convolution and correlation. In convolution it will be x1 of z into x2 of z. Here you have an z raised to minus 1. So you may do this by yourself, the proof. Okay, I am not going to do that. Okay, now next thing is initial value theorem. What is the meaning of initial value theorem? Say suppose you consider an x of n. The meaning of initial value theorem is what is the value of x of n at n is equal to 0, or in a more technical way you can say that the value of x of n as limit n tends to 0, right? So that is your initial value. Now in order to apply this initial value theorem, this is applicable only for a one-sided z transform, okay, or a right-hand sided z transform, or that is called as x plus of z. What's the meaning of that? This is the z transform of only causal sequence. So we know that x plus of z will be a right n is equal to 0 to infinity x of n z raised to minus n. So you are making use of that expression. X plus of z is this thing. You can have an expansion like this, x of 0 plus x of 1 into z raised to minus 1, etc. So the same thing can be written as x of 0 plus x of 1 by z, x of 2 by z square. Okay, now this is actually limit as n tends to 0, that is timing tending to 0 means z tends to infinity. Now what happens when z tends to infinity to this expression? X plus of z becomes, this z becomes infinity, meaning this term becomes 0. All the rest of the terms become 0, leaving x of 0 itself. So what is x of 0? X of 0 is the initial condition, initial value of that function, that is nothing but x plus of z tends to infinity. So what is the so this is actually your initial value theorem. And what is the significance of initial value theorem? So suppose a signal whose z transform is given, you don't need to convert it into its x of n to find its initial value. You just need to apply what is that limit z tends to infinity, and that resulting value is going to be the initial value of that function. The only thing is that it is applied only for a right hand side RH right hand sided is a transform, or single sided is a transform. Okay, now coming to the 13th property, which is the final value theorem. Just as we see in the initial value theorem, there is also some restriction. That is, first of all, it has to be a single sided is a transform. This is valid for a single sided or positive going is a transform. So, and another important point is your x plus of z, meaning only single sided, your x plus of z is of the form p of s by q of z form, right? P of z to q of z form. When you equate q of z to 0, what you are going to get, you will get some poles, right? So which we have studied in Laplace transform. So all these poles, the condition of this is, in z plane there is a circle, unit circle, right? And this unit, I mean, all these poles should remain inside the unit circle. That is, these poles should not reside on the circle as well as exterior to the circle. It should be, all the poles should reside in the inside of the circle. So this is the requirement for an x plus of z to have a final value. Now what is the meaning of final value? Final value is, so you have a time domain signal. Now when you substitute infinity, the value that you are going to get for that particular x of n is the final value. Now now the importance of this theorem is, even if you have x plus of z, even without the knowledge of x of n, you can find this value by using this x plus of z. That's what we are going to prove. And the proof is, final value theorem states that the final value of the time domain function is nothing but x plus of z multiplied by z minus 1 as limit z tends to 1. Okay, now to start with, we start with the given signal x of n that gets subtracted from its advanced version by 1. So x of n plus 1 is the advanced version, x of n plus 1 minus x of n. So what is the z transform of this? So you can use the basic expression. Why n is equal to 0 to infinity? Because it is x plus of z. X of n, this is the assumption, x of n is having the x plus of z. So n is equal to 0 to infinity, x of n plus 1 minus x of n, z raised to minus n. Now what is this? But now let us move on to the left hand side. Now when you have the z transform of x of n plus 1 minus x of n, it is nothing but z raised to, we have seen the special case of time shifting. Using that, you can find out it as z raised to m. So instead of m, you have 1, z raised to m into x of z minus z raised to m into x of 0, that is small x of 0. That is, it is actually sigma k is equal to 0 to m minus 1. Here m minus 1 is 0. So 0 to 0, you will be having only one value. So you can just refer that, which I have taught you in the previous videos. So z into x of 0 minus, this is small x of 0 minus x of z, right? What is this? X of z means the z transform of this x of n. So you will be getting, and now you can equate to this right hand half. So this is equated to the right hand side, and what happens is you can combine these two x of z. So combining these two x of z, you will get z minus 1 into x of z minus z times x of 0 is equal to sigma n is equal to 0 x of n plus 1 minus x of n into z raised to minus n. Okay, now applying the limit as z tends to 1. Now you cannot apply the limit here because we do not know anything about x of z. After simplification only we can apply. So you must keep there as such. So applying limit z tends to z. Now this z becomes 1 because there is no other z value, or this is a time signal. So you can just make this z to be 1, and similarly in this case also, in this side also you can make this z to be 1, so that you will get this expression, right? Now you can expand this. Now what happens when n is equal to 0? This becomes x of 1 minus x of 0. What is the second term? Second term is when n is equal to 1, this becomes x of 2 minus x of 1. And if you can write up to infinity, so up to this infinity, you can see only two terms survives. That is, one is x of infinity and one is x of 0. I will explain how it is. So if you have an x of 1, there will be a minus x of 1. You cannot find a plus x of 0 here, right? So this x of 0 survives. All other terms up to infinity will get cancelled except x infinity. So this will be x of infinity minus x of 0 is equal to limit z tends to 1, z minus 1 into x of z minus x of 0. This x of 0 and x of 0 get cancelled, so resulting in this x of infinity. So this is your final value theorem. Okay, now let's do some special problems. So let's try to apply the some of the properties which we have studied so far. Find the Z transform of the following signals using suitable properties. So number 1 is n into u of n. Now we have already studied that for in the differentiation or n times multiplication by n times, or the differentiation in frequency domain property, you may refer that property. So in that property we studied that if you have an x of n with z transform x of z, n times x of n will be the derivative of this into multiplied by minus z. So in this case it is n into u of n. We know the z transform of u of n. So that is why I told you to study some of the standard signals is a transform. So the is a transform of u of n we have already derived using the basic expression. You may just refer to that if you are not aware of this. So the z transform of u of n is z by z minus 1 with ROC mod z greater than 1. Now what you need to do to get n into z transform of n into x of n, first of all you need to take the derivative of that, multiply that derivative by minus z. So taking the derivative and applying so you should take the derivative of this, right? X of z, taking the derivative, that is x of z is minus z into d by dz of z by z minus 1. Taking the derivative and multiplying by minus z, you will be getting, you may just do it by yourself, you will be getting z by z minus 1 the whole square, where mod z is greater than 1. Now you can just represent that by drawing a circle with radius 1, and the shaded portion is to be the exterior region of that circle, which is the ROC of this problem, ROC of this transform. Now another problem is of the same type. Sometimes you may be asked a question like this: apply suitable properties. So whenever you are asked to apply suitable properties, you are not supposed to use the basic expression, you need to apply the properties. So n into a raised to n into u of n. Okay, now you can either you can start with the u of n. U of n is z by z minus n mod z greater than 1. Now you have studied about multiplication by exponential sequence property, that is a raised to n into u of n, that this has to be replaced by a inverse z. Okay, so similarly a inverse z will be here, so z will be greater than a, z by z minus a. Okay, so you can apply that. Now this is also a standard form, so you don't have to start like this. If you know the standard form, a raised to n into u of n is z by z minus a mod z greater than a, this also we have derived. So if this is the standard form, then you can straight away apply n times means taking the derivative of this multiplied by minus z. So while doing that, you will be getting a z by z minus a the whole square with the ROC to be mod z greater than a. Okay. Okay, and next is find the z transform of a raised to n minus 1 into u of n minus 1. Okay, now but we know the z transform of a raised to n into u of n. So that is your basic expression, that is z by z minus a mod z greater than a. Okay, now if you know that, what is actually this? If you call this as your x of n, okay, and that must, then this must be your x of z. So what must be this? What must be the question? The question is nothing but it is x of n minus 1. You are shifting that. Now from the time shifting property, you know that it is this is what is called as a time shifting property. X of n minus k is equal to z raised to minus k. So just multiplying this z transform by z raised to minus k, where k is equal to 1, right? So z minus 1 into z by z minus a. This is 1 by z minus a. Now we know that ROC is mod z greater than a. So if you are time shifting, there is no, I mean, the ROC is not going to change. Still it is mod z greater than a. Is, as I told you earlier, this is a circle with a draw a circle with an arbitrary radius a. Shade the exterior region to mark its ROC. Okay. Now the next problem is a special type of problem. You are asked to find out the inverse z transform of this problem, x of z. Okay. So you are asked to find out the inverse. Inverse means when you take the inverse, you will get x of n. So x of n is the inverse of x of z, and where x of z is the logarithm of 1 minus a z inverse, mod z greater than a. So you don't have any direct method to find out this inverse z transform of such problems. So it is a sort of indirect methods. So I mean, if you want to do such problems, you need to do exercises, lot of exercises, then only you will be able to understand at the right time how to proceed with. Now this is bit indirect. Now how to proceed with this? You can take the derivative of this. Okay, that is dx of z by dz. Okay, so what is the logarithm? Log of x, derivative of log is 1 by log x. So when you take the derivative, this is 1 by a z, and taking the derivative, it will be a z raised to minus 2, a into z raised to minus 2 by 1 minus a z inverse. Now what is minus z into dx of z? Minus a z, you are multiplying again by z raised to minus 1, so resulting is minus a into z raised to minus 1 divided by 1 minus a z raised to n minus 1. Now from the derivative property, we know that if this is minus z dx of z, this must represent, this is actually the z transform of what? N into x of n. Okay, so from this, if you can find out the inverse of this, you will be getting n into x of n. So that's the idea. So if you can some way or other, if you can find out the inverse of this thing, this quantity, you will be able to find out n into x of n, right? So what is that? Let us look into it. So minus z, I have rewritten that again, a minus a z inverse of taking this outside, minus of 1 by 1 minus a. So this can be written as z by z minus a. Mod z is greater than a. So what is this? Z by z minus a is z by z minus a is the z transform of a raised to n into u of n. Okay, that z transform is multiplied by z raised to minus 1 means it is time shifting. So this will be the z transform of a raised to n minus 1 into u of n minus 1 into a simple constant. So there is nothing wrong in taking this inside this minus a into a n minus 1, or you will be getting minus a into a raised to n into u of n minus 1 by n is going to be what? It is actual, I mean, this quantity will be equal to n times x of n, because we know that minus z into dx of z is actually the z transform of n into x of n. So if you get the inverse of this, what you are going to get is n into x of n. So n into x of n is this. So if this is n into x of n is divided by n. So so you may just work out by yourself and arrive at this result. Okay, now one more problem, that is you have two signals, x1 of n into and x2 of n, 1 by 3 raised to n into u of n and 1 by 5 raised to u of n. Okay, this is of the form a raised to n into u of n. Okay, so using that you can so you need to apply, you need to specify the property, the exponential multiplication. So z by z minus 1 by 3, z by z minus 1 by 5, mod z greater than 1 by 3 and mod z greater than 1 by 5. So what will be the z transform of the convolution? It will be the product of this, right? x1 of z into x2 of z, that is z by z minus 1 by 3 into z by z minus 1 by 5. What will be its overall ROC? The overall ROC is going to be the intersection, and since 1 by 3 is greater than 1 by 5, this has to be greater than 1 by 3. It has to be great, mod z is to be greater than 1 by 3. Okay, so That's it. Okay, now the next question is find out the final value of the function x plus of z is given by z plus 2 by z minus 0.8. So what you need to look is obtain the poles of x plus of z. You can see that z is equal to 0.8. You have two poles, right? Z minus 0.8 is, you have two poles residing at 0.8, which is well within the unit circle. Now if it is well within the unit circle, this has final value. So how to find out the final value? Multiply this by z minus 1 and apply the limit as z tends to infinity. So no terms got cancelled, only you have z minus 1. When you apply 1, you will be getting 0. Now another problem, x plus of z is 3z plus 4 by z minus 1 into z plus 1. When you find out the poles, that poles lies on the z is equal to 1 boundary, right? So it is not possible to have a Fourier transform or Fourier it is not possible to have a final value. Therefore the final value is undefined in this case. Okay, now you may just refer your textbook to see various problems. I think there are a lot of solved examples as well as unsolved examples, and you may try to do it by yourself. I think the most important thing that you need is the practice of this problem. Then only you will be able to do a new type of problems regarding Z transform. Okay, good luck.